All right, so in this video, we're going to be talking about complex similarity transformations that will turn your matrix into a rotation matrix. Not all matrices are diagonalizable, and one situation that can happen to make your matrix not diagonalizable in the real matrix space is when your eigenvalues are complex and not real. And so what's going to happen when you have those kinds of transformations is that they're not going to have principal directions in which they stretch a vector like a scalar. Instead, they're going to be rotating the matrix and also stretching it. So we're going to be looking at how to figure out what the rotation is, what the angle of rotation is, and we're going to need to find a matrix C, which represents that rotation. And we're also going to need to find the transformation that makes that possible. Now, the theorem that we're going to use, since we are making a counterclockwise rotation, is we're going to use the complex eigenvalue A minus BI in order to create our matrix. And then our C matrix is going to be equivalent to a rotation where we have, we would think of this as equivalent to scaled versions of cosine and sine. And so this is the same place we would expect to have minus sign on the top row and positive sign on the bottom row like this. So sometimes this can be a little tricky because we were essentially ignoring this minus sign, but there is a minus sign still in the matrix. And if you switch the order of the where the sign is supposed to go, you will turn it into a positive clockwise rotation instead of a positive counterclockwise rotation. But let's walk through the process. Again, we're going to use a 2x2 matrix, partly to simplify the situation, but also because you need 2 dimensions in order to do a rotation. You can't really do a 3-dimensional rotation all at once. You have to think of it as rotating on these 2-dimensional axes and then rotating again on another 2-dimensional axes. And so every rotation is fundamentally going to have an angle that's in a plane. So 2 of the axes will represent the rotation. And then if you have a 3-dimensional matrix, for example, you would have to have 1 real root. And so you could only be rotating in one direction and then scaling in another. You can only rotate in 2 directions, really, if you have 4 dimensions. It's very complicated. So let's go through the 2-dimensional case, and then we'll worry about extending it to larger dimensions in another lesson. So first, we're going to try to find our characteristic polynomial, and we're going to try to find our eigenvalues. So we're going to calculate our A minus lambda I matrix. So this is going to be -1 minus lambda and 2 and -5 and 5 minus lambda. And so if we find the determinant of this, we're going to have -1 minus lambda and 5 minus lambda, and then plus 10 equals 0. And when we multiply this all out, we're going to have -5 and plus 1. That's going to be -4 lambda in the middle. And then -5 plus 10 is going to be 0. And so that's going to give us lambda squared minus 4 lambda plus 5 equals 0. So now what we're looking for are factors of 5, which we're going to add to 4. No such thing exists. And so we are going to need to use the quadratic formula right here. But for our lambda, and when we plug everything in for that, let's see, b is going to be -4, so that's going to be 4, and so that's going to be 16, and this is going to be 20, and that's just a 1. And so we're going to end up with 4 plus and minus. 16 minus 20 is going to be the square root of -4, which is going to be 2i divided by 2. So that's going to be 2 plus and minus I. So the lambda we want to work with is going to be 2 minus I. And so we need to find the eigenvector that corresponds to that. Let's put together our C matrix since we have what we need for the C matrix already. So A is 2 and B is 1 because the minus sign is part of the version of the eigenvalue that we want. And so that minus is part of the formula rather than part of the B, part of the constant. So this is going to be 2 minus 1, 1, 2. That's our C matrix. And then we need to find our transformation matrix, our similarity transformation matrix. And so that is derived from the eigenvalue that corresponds to this lambda. Now, we could find both of them because they're complex conjugates of each other. And so if we find one, we will know the other, but we're just going to directly go ahead and find the one that we're looking for. So -1 minus 2 minus I, and 2, and -5, and 5 minus 2 minus I. And so if we simplify, that's going to give us -1 and -2 is going to give me -3 plus I. And this is going to give me 2. And this is going to give me -5. And this is going to give me +3 plus I. And again, this is a very common thing that you'll encounter with complex eigenvalues and eigenvectors. These aren't conjugates on the diagonal here because it's the real part that is being flipped for the sign, not the complex part. But that is what you would expect to see when these are multiples of each other. You can go ahead and like multiply by the conjugate to make this real, and then it would be easier to see that these are in fact multiples of each other. But I'm going to assume that I haven't made any major arithmetic mistakes and that these are correct. And I'm going to take the bottom equation so I don't have to divide by complex numbers. X1 plus 3 plus I, x2 is equal to 0. That's my dependent equation. And if I solve for this, I'm going to end up with x sub 1 is equal to, I will have a -3 plus I x2, but then I'm going to divide by -5. And so the negatives are going to cancel. And then my second equation will be x2 is equal to itself because it's in the null space. And so V is going to be equal to, and I'll let x2 be 5. So the numerator is 3 plus I, and then the 5 will cancel out the denominator. And the real part of V is going to be 3 and 5. And the imaginary part is going to be 1 and 0. Times I. And so my P transformation matrix should be 3, 5, and 1, 0. And so now what is left is to find out if this in fact works, or if I need to multiply in the reverse direction. So let's find out what P, C, P inverse is equal to. So this is P, and this was C, and then P inverse, it's going to be 1 over -5, using my formula for 2 by 2 inverses. We're going to flip the order, so 0 and 3, and then flip the sign, -5 and 1, and then let's see what happens. I'm going to move the -1/5 out front. We'll deal with it later. And so if I multiply my first two matrices together, I am going to get 6 plus 1 is 7, and -3 plus 2 is 1, and that's 10 plus 1 is, or plus 0, and then -5 and 0 is -5. And then if I multiply again, zero and -5. I think I have to multiply in the reverse order, perhaps. No, well, the -1/5 might fix that. Let's continue. Yeah, so 0, and that is -5, and then multiplying over here is 7, and 3 is 10, and 10 and 0 is 0, and -5 and 5 is 25, and 10 and 3 is going to be 30, and sorry, 10 times that is 10, and then -5 times 3 is going to be 10, and -15 is going to be -5. Yeah, that doesn't quite seem to work. Let's check my calculator. And I found my mistake. This inverse is a -1. I have to flip both of those signs, and I only flipped the one. That will fix that. That'll make that -25. And that will also actually change this sign as well. Yep, that'll fix that. I was wondering what was going on there. And so Now, when you multiply by the negative 1/5, you do in fact get back to our original matrix, which was -1, 2, -5, and 5. Yeah, so don't lose those minus signs. Check your work and make sure that everything works out correctly. So P, this is our similarity transformation, and C is our complex rotation matrix. So what is the angle of rotation that we got from our C matrix? Well, if this is C, remember what we're essentially comparing this to is the rotation matrix that was cosine theta minus sine theta, sine theta, cosine theta. Now, the problem is that our two entries are not right now currently having values less than 1. So I can't just take the inverse cosine of 2 because that isn't correct. But this is a scaled rotation matrix. So it's rotating and stretching. So what we need to find is essentially this matrix, but it has R in it. So it's a scaling factor, R cosine and R sine and R sine here and R cosine there. So what we're going to do is we're going to find R. So R is R squared, right, is cosine squared plus sine squared. So it's our two entries together. It's 2 squared plus 1 squared. You can use the rows or the columns, whatever, because the signs are going to cancel when you square them, which is equal to 5, which means that R is equal to the square root of 5. And so we can take that out of our matrix as a scaling factor, put that outside, and then inside we will have 2 over the square root of 5 and -1 over the square root of 5 and 1 over the square root of 5 and 2 over the square root of 5. Now, since we want an angle that is in the first or second quadrant, since we're going counterclockwise, we can just use inverse cosine of 2 over the square root of 5 from that first entry. You can also, of course, take the inverse tangent, and then you would get an angle in either first or fourth quadrant, and then you would have to move it into the second quadrant if need be. So this is just a little easier. 2 divided by the square root of 5. This is not going to be a pretty angle, but that's fine. In degrees, this is approximately 26.565 degrees, or if we switch back to radian mode, then this is approximately 0.463647 blah 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 radians. So it's a positive value. It's in the first quadrant, but we're rotating our matrix, our vectors, by about 26 degrees when we multiply by this matrix, 26.5 degrees. And then we are also stretching them by a factor of the square root of 5.